Welcome to the second video of M3302. So in this video, we are going to start with Chapter 1. Chapter 1 has 4 sections. First section that we shall cover in this video, norm spaces and Banach spaces, mostly a review. Section 1.2, linear bounded operators. Section 1.3, multilinear bounded operators. And we shall end with a review on Hilbert spaces. Okay, so definition: if E is a real vector space, so all spaces in this course will be real, so there will be vector space over the field R. Because there is another theory for complex valued vector spaces, and that it's connected to the theory of holomorphic functions that we shall not cover in this course. So a norm on a vector space is a function that associates to each vector x, each element of E, a non-negative number denoted by this double bar, and which satisfies 3 properties. It's 0 if and only if the vector is 0. And second property is homogeneity. So when we multiply, the norm of a multiple of a vector is a multiple of the norm, but with an absolute value because lambda can be negative. So norm of minus x is also norm to x, is equal to norm of x. And the last property is the triangle inequality. So the norm of the sum is less than the sum of the norms. And there is another form of condition 3 known as the second form of the triangle inequality. It reads, so we can replace condition 3 with this condition, 3 prime. The absolute value of the difference of the norms is less or equal than the norm of the difference for any 2 vectors x and y. So we can prove that 3 implies 3 prime and 3 prime implies 3. Okay. So a norm space is a vector space equipped with a norm. It's also called norm linear space or norm vector space, but for simplicity, we'll just say norm space. Okay. And now, as you may know, if we have a norm on a vector space, a norm defines or induces a distance. So if we set d of xy equal the norm of the difference between x and y, then d is a distance, as you may easily check, because recall that the distance is something non-negative, it's symmetric, it's 0 if and only if the 2 points coincide, and we have the triangle inequality. And therefore, a norm space is a particular case of a metric space. A norm space is a particular case of a metric space, and therefore, it's a particular case of a topological space. So in a norm space, we have the notion of open ball, open set, closed set, compact sets, convergence, and so on. Okay, notational review. The open ball of center A and radius R is the set of elements x whose distance to the center is strictly less than the radius. And the closed ball of center A and radius R is the set of elements x whose distance to the center is less or equal to the radius. And we can prove that the closure of the open ball is equal to the corresponding closed ball, and the interior of the closed ball is equal to the corresponding open ball. These relations do not hold in an arbitrary metric space. Okay? And they are not totally trivial to prove, but I think you encountered the proof somewhere. If you don't believe me, because actually most of the result in this video will be given without proof, because in principle you encounter them in second year. Okay, so if you forgot them, you have 3 options. Either you accept them, or you prove them, which is very good, on your own, or you read the proof somewhere in books or in you review your course of second year. But it makes no harm of reproving known things. Okay, it's a good exercise. So here, how do we prove that? Double inclusion. Okay. A Banach space is a complete normed space. which means that every Cauchy sequence is convergent. And now, as usual, I will give a series of examples, fundamental examples that in principle you encountered, but we shall review them. So if n is an integer which is at least 1, and p is a real number which is at least 1, Rn, r to the n, is what? Is the Cartesian product of n copies of the real line. So an element of Rn is just an n tuple having n components. So we set the norm p of x to be the sum of the pth power of each component in absolute value, and everything raised to the power 1 over p. So when p equal 1, we just have the sum of the components in absolute value. If p equal 2, we get the Euclidean norm, the usual norm that you are familiar with. Okay, but this can be defined for any p. So we have a collection actually of norms. So this is really a norm because we can prove that it satisfies the 3 properties of a norm. But this is not, the first 2 properties are a little bit trivial, but the triangle inequality is less trivial. It follows from another inequality called the Hölder inequality. Okay, but I'm not going to prove that. So the result is that this defines a norm, and Rn with this norm is a Banach space. Now, the other extreme case, what happens if we let p tend to infinity? We can prove that when p tends to infinity, the norm xp tends to this norm, which is defined by the maximum of the components in absolute value. So once again, Rn, this is a norm, and Rn with this norm is a Banach space. And just 2 remarks. Actually, what makes this space a Banach space? Because Rn is finite dimensional. So in general, any finite dimensional norm space is complete. Okay? In principle, you prove that. You can prove it if you like. Because we have a basis, a finite basis. Okay? And R is complete. Okay, so if we have a Cauchy sequence, then each component of the sequence is a Cauchy sequence in R. Since R is complete, each component converges. This is the idea. And as we said, we can prove that when p tends to infinity, the norm p of x converges to the norm infinity of x, hence the notation. So the norm infinity is a particular and extreme case of this collection of norms. Okay, third example, less trivial. An example of an infinite dimensional space is the space of sequences. So a point here in that space is a sequence. It's an infinite sequence. So it's a list, x1, x2, etc. Satisfying this condition if p is bigger or equal than 1. So small lp is the set of sequences such that the series whose general term is xn to the p is convergent. So this is just another notation for meaning that to denote convergence of this sequence. Okay. So this is a vector space actually. It's not difficult to prove that because the sum of 2 elements in LP is again in LP, and when I multiply by a scalar, the result is in LP. Okay. This follows actually from what is known as Minkowski's inequality. Okay, so this is an example of an infinite dimensional vector space. And when you put norm of xp to be the sum of all components to raised to the power p and everything raised to the power 1 over p, we get a norm. And the triangle inequality, by the way, is known as Minkowski's inequality. Okay, so we get a norm, and we can prove that when LP equipped with this norm is complete. Okay, and the extreme case, L infinity, how to define L infinity? L infinity is the set of all bounded real sequences. Okay, so again, it's a vector space. And if you set norm infinity to be the supremum, note that here the supremum need not be a maximum, okay, because it's an infinite list. So this is a norm, and it makes L infinity complete. Okay, so these are fundamental examples of sequence spaces. Okay. Fifth example, space of continuous functions defined on an interval AB. It's denoted by CAB. This is notation is famous or well spread among functional analysts. So we can put CAB between parentheses, but in order to simplify the notation, we can remove the parentheses, okay, for simplicity. So CAB is the set of continuous functions from a closed interval AB into R. So as you may check, this is a vector space, okay, because the sum of two continuous functions is continuous, multiple of a continuous is continuous. And the norm on the space, the infinity norm or the supremum norm, or the norm of uniform convergence, also called. So the norm of an element f is the supremum, which is a maximum actually, because f is continuous on this compact set, so it has a maximum value and the minimum value as well. So the maximum value of an absolute value, we have to take the absolute value because this should be something non-negative. Okay? If we drop the absolute value, it's no longer a norm. This is what we call a semi-norm, or not a semi-norm, a subnorm. Okay. So this is a norm, and it's a fundamental result that this norm makes CAB complete. Okay. So not trivial. It requires a proof. So once again, either you accept it or you prove it or you read the proof somewhere. C1AB usually denotes the set of continuously differentiable functions f from AB to R. So we have a continuous, so each element in C1 has a continuous derivative. So once again, this is a vector space. And if we take the maximum of the absolute value of f plus the maximum of the absolute value of f prime, so we apply this to f and f prime, and we do the sum, then we get a norm. And this norm makes the space complete. Okay. Now, an example of a non-complete Banach norm space. So, for any p, which is at least one, and a real number p, and if f is continuous, then we put norm p of f to be the integral. Sorry, there's an error here. It should be raised to the power 1 over p, because there's an error here, so please correct it. And so we get a norm, and now, however, this norm is incomplete. How do we prove that? It's enough to find a Cauchy sequence, a sequence of continuous functions, which is Cauchy in this norm, but that converges to a discontinuous function. This is the idea of the proof. Okay, so there's 1 over raised to the power 1 over p. So this space is not complete. Okay. And once again, you can prove that as p tends to infinity, the norm p of f converges to the maximum norm or infinity norm or norm of uniform convergence. Now, why do we call it norm of uniform convergence? Because convergence in this norm is equivalent to the uniform convergence of the sequence. Okay, and last example, if you have an arbitrary set x and an arbitrary norm space y, we denote by C sub b of xy the set of all bounded functions f from x to y. And of course, this is a vector space because y is a vector space. Okay, so the sum of two functions is defined the usual way. So f plus g of x is f of x plus g of x, and multiple same thing. So, and now again we define the infinite norm of f as being the supremum of the norm of f of x. Okay, because this is the norm in y, because f of x is an element of y. So we get a norm, and if y is complete, then CB of xy is complete as well. Okay. And as I mentioned before, all the examples, or the spaces in example from 3 to 7 are infinite dimensional. Okay. Which means what? Which means that we can find in them arbitrarily large linearly independent sets. Now, I shall not focus or dwell on this notion of infinite dimensionality because we shall review it next year. We'll not need it in this course, but you have to know that most of the interesting spaces in analysis are infinite dimensional, unlike the spaces of linear algebra that you studied in first year. Okay, now try to think of this if you like, but we shall not return on this point. Now, remark, we say that, so in a normal space, we can talk about convergent sequences, as we said, and you can talk about convergence of series, because in a normal space, in a vector space, we have the notion of sum. So the series is convergent if the sequence of partial sums is convergent. Now there is another mode of convergence called normal convergence. So a series is normally convergent if the series of norms is convergent. Okay? And now we have this result. We have an equivalence. So E is complete, a norm space is complete if and only if every normally convergent series is convergent. Okay? If we take E equal R or Rn, then this is true. And normal convergence in R is called just absolute convergence. So you know that in R, absolutely convergent sequences are convergent. The reason is that R is complete. Okay? And in this case, if E is complete, then we have a normally convergent series, then the norm of the sum of the series is less or equal than the series of norms, the sum of the series. Okay? So this is a kind of triangle inequality, but we allow to add infinitely many terms. So, but under the assumption of convergence, of course. Okay, and now we go to the notion of equivalent norms, which is very important. If we have a vector space E, and we have two norms, norm 1 and norm 2 on E, we say that these two norms are equivalent if we can find two positive constants, alpha and beta, such that the norm 2 is bounded from below by alpha times norm 1 and bounded from below by a constant times norm 1. So as you may check, this is an equivalence relation between norms. So we have reflexivity, symmetry, transitivity. Okay. And let me just recall some results concerning equivalent norms. So if you have two norms on a vector space E, then the following conditions are equivalent. So one can be deduced from the other. First condition, the two norms are equivalent in the sense that I gave here. Second condition, norm 1 and norm 2 generate the same topology. What does this mean? We know that a norm defines or generates a distance, and the distance generates a topology. Okay. So an open set is open if every point in the set is the center of a ball totally contained in the set. Okay, so a norm generates a topology. So the two norms are equivalent if and only if they generate the same topology. And this is also equivalent to the third condition, that the identity operator from E to E is just the map that to each x associates x itself. So this is the identity. But here, if we equip the source space with norm 1 and the target space with norm 2, we get a homeomorphism. Okay? So these three conditions are equivalent. A useful result. And you can prove that if this is the case, if the two norms are equivalent, then E with norm 1 is complete if and only if E with norm 2 is complete. Okay, so they are both complete or incomplete simultaneously. Okay, so if one is a Banach space, the other is a Banach space. This is not difficult to prove. You can prove it if you like. Now, you probably also proved that on a finite dimensional norm space, all norms are equivalent. Okay, the main reason of this is the compactness of the unit sphere, because the unit sphere is closed and bounded, so it's compact. Okay, so this is also, if you can prove it if you like, good exercise. So there are two big ideas in the proof of this important result. So first, as I said, the compactness of the unit sphere, and second thing is the existence of a minimum value of a continuous function on a compact space. Okay, so two important results in topology. Now let us revisit the notion of a product of two normal spaces. So if you have two normal spaces, E and F, we can define several norms on their product. The product is just the set of couples. So first one, norm 1 of a couple xy is the norm of the first component plus the norm of the second component. And the first component is in space E, and second component is in space F. So we can take the sum, we can take the maximum, we can take the Euclidean norm if you like. And therefore, in this case, we can prove that all these norms are equivalent, and they generate what is called the product topology on the product of two topological spaces. If you didn't encounter the notion of product topology, don't worry, just take any norm. So all these norms are equivalent. And if the two spaces are complete, then their product is complete. Take any norm. Okay, we said that all these are equivalent. So if one is complete, the other is complete. So it's irrelevant which norm we take. And more generally, if you have an arbitrary but finite number of norm spaces, we can define their Cartesian product, the one norm which is the sum of the norms of each component, the maximum, and the Euclidean norm. And once again, all these norms are equivalent, they generate the product topology, and if all of them are complete, their product is complete with respect to any of these norms. Okay, now I will mention a result that you may have proved. If you have a norm space and you equip the product of E by itself by any of the norms, so for example, the one norm, which is the sum of the components, and we consider two operators. The operator T that to each couple lambda x, lambda in R and x in E, associate the product. So this is multiplication by scalar. And when you consider the operator sum. So now E is a norm space, so it's a topological space. This is also a norm space, it's a topological space, same thing here. So we can talk about continuity. Continuity here, because all these sets are metric spaces actually. So continuity is just what we call equivalent to what we call sequential continuity. So to prove, for example, that T is continuous, it's enough to prove that, so we have to prove that T is continuous at every point lambda x. So we take an arbitrary point lambda x in this product, and we consider an arbitrary sequence lambda nxn converging to lambda x. We have to prove that T of lambda nxn converges to T lambda x. Okay, so T takes convergent sequences into convergent sequences. Okay, so now by definition, or it follows actually from the definition of this norm, that if lambda nxn converges to lambda x, then each components converge to the corresponding components. This is actually equivalent to the continuity of projections, if you like. So if lambda nxn converges to lambda x, then the first component converges to the first component, second component converges to the second component. It's not difficult to prove. And now I use the triangle inequality. So T lambda nxn minus T lambda x is by definition lambda nxn minus lambda x. And if I add and subtract lambda nx and apply the triangle inequality, I get the first term is lambda n xn minus x because I factor by lambda n. And the second term I factor by x. And now I use the properties of a norm. So I can put the lambda n outside, but in absolute value. And here I can put lambda n minus lambda in absolute value, but outside. And now if you consider the first term, xn minus x in norm converge to 0 because xn converges to x in E. And lambda n also converges, minus lambda converges to 0 because lambda n converges to lambda. Now, what about this term, lambda n? This term actually is bounded because the sequence is convergent. So I'm multiplying something that tends to 0 by something which is bounded. So this term tends to 0. This is a constant now, and this term tends to 0. So the first term tends to 0, and the second term tends to 0. And therefore, this difference tends to 0. And therefore, T takes convergent sequences into convergent sequences. Okay, so this proves continuity at the point lambda x. But since lambda x was arbitrary, this means that T is continuous everywhere. Okay, and now the proof for the continuity of S is similar, but a little bit easier. You don't have to use this trick here. Just do the same thing, a little bit easier. So following the same lines, we can prove that S is sequentially continuous and therefore continuous. Okay, so if x n y n converges to x y, then the sum converges to the sum. So almost trivial. Okay, and I will end this video with a review of a very important notion, the notion of convexity, that we shall revisit later when needed, when we will talk about convex functions, not only convex sets. But let us first review the notion of a convex set in a vector space. So if A is a subset of a vector space, we say that A is convex if any convex combination of two elements of A is still in A. Because this is called a convex combination. So it's something of the form 1 minus tx plus ty, or if you like, alpha x plus beta y, where alpha plus beta equal 1 and alpha and beta are non-negative. So same thing. So this is a particular case of a linear combination, but a convex combination is more restrictive. In linear combinations, we allow arbitrarily large. We don't put a restriction on the coefficients, but here we put that the restriction that the coefficients should be non-negative and between 0 and 1. Okay, so this is called a convex combination of x and y. So convexity means that the straight line segment, okay, because this is the equation of a straight line segment. Any point, by definition, actually, a point in the straight line segment joining x to y is by definition the set of all these convex combinations. So convexity means that the straight line segment joining any two points in A is totally included in A. Okay. So in particular, keep in mind that subspaces are convex because subspaces are stable under arbitrary linear combinations. So in particular, under convex combinations. And any kind of ball in a normed space is also convex, as you may check by going back to the definition. So I just did this review because there's an exercise about convexity that you will solve next week. But we shall revisit this later when needed. Okay, I don't want to overburden you with so many things. So this concludes this video about section 1.1, normed spaces and Banach spaces. Okay, in the next video, I'm going to cover linear bounded operators, a very important concept as well. So thank you for your attention and see you next time.